Have you ever thought about the sheer amount of invisible, high-stakes communication happening behind the scenes of a massive industrial plant? I mean, behind all those giant steel pipes, fluid tanks, and chemical reactors, there is literally a constant stream of digital chatter. And the stakes? Well, they're incredibly high. Just one missed morning could trigger a massive cascade leading to a full-blown plant shutdown. Today in this explainer, we're diving into the brilliant architecture that actually prevents that from happening, the somatic Pcs7 message system. We're going to see exactly how engineers design these industrial interfaces to take total chaos and turn it into absolute clarity. Let's get right into it.
So here's our roadmap for the journey today. We'll cover 1. The central nervous system, 2. Anatomy of an alarm, 3. Taming alarm fatigue, 4. The synchronization triad, 5. Analytics and optimization, and finally, number 6. The message lifecycle.
All right, kicking things off with part 1, the central nervous system.
You can really think of the Pcs7 system as being like a biological central nervous system. It constantly takes in this totally overwhelming amount of raw sensory data from the physical plant and translates it into something the human operator in the control room can actually understand and use. This entire nervous system is driven by 4 absolutely critical outcomes. First up is comprehensive status, giving the operator complete visibility into all faults and operating modes. Second is early detection. We're talking about instantly flagging critical situations and limit violations before they ever escalate. Third is downtime prevention, which is all about proactive mitigation. And finally, quality assurance. This ensures tight adherence to process parameters, so the final product comes out flawlessly. Honestly, without these 4 pillars, operators would literally be flying blind in a highly volatile environment.
Now, to manage all that data, the ecosystem breaks messages down into 3 main categories. First, we have process control messages. These are your hardware or system errors, think of a physical wire snapping or an I/O module failing. The system's driver blocks generate these completely automatically. Next up, we have process messages. These are triggered by automated process events, like when a measured value crosses a specific threshold. And finally, operator messages. These are logged the moment a human intervenes. So if an operator tweaks a process quantity using the libraries, the system automatically generates a permanent record of it.
Moving right along to part 2, anatomy of an alarm. So, what does an alarm actually look like when a physical event triggers a digital response? Picture a massive physical fluid tank. As the liquid level rises, it doesn't just trigger an alarm out of nowhere. The physical realities of that tank are precisely mapped to a digital limit stack. On the interface, specifically using the All-I-Know-Is faceplate, operators look at a mirrored digital limit stack. Down at the bottom, you have your alarm low and warning low, and up top, your warning high and alarm high. The exact second one of these limits is breached, an output parameter is set. And what's really cool is this direct mapping lets engineers enable or disable limit monitoring entirely independently from the actual message generation itself.
Okay, so when that limit is breached, boom, it generates a message line. Let's break down the actual anatomy of this line so we don't get lost in the interface. First off, you've got the timestamp and priority, which gives you an exact chronological log and an urgency ranking. Then there's the message class and type. This acts as a visual indicator of severity, like, say, highlighting an alarm high in bright red. Third is the configured event text. This is the human-readable part, something like high warning limit violated, so you actually know what just happened. And finally, the message status. This simply tells the operator if the alarm is incoming, outgoing, or if it's already been acknowledged.
But here's the thing, an alarm is really only useful if you actually know how to fix the problem, right? And that is exactly where help techs swoop in to save the day. Attached to specific messages, these pop-ups give operators plain language context to stop a disaster in its tracks. It'll tell you the expected reaction time, like 0 minutes, meaning drop what you're doing and fix this right now. It gives a clear description and cause, like reactor overheat. Most crucially, it outlines the exact suggested user action, literally spelling out the mechanical steps, such as close heating valve TIC315 immediately. And it brutally lays out the consequences of ignoring it, letting you know the reactor will be overheated and damaged. It totally removes the guesswork during a high-stress crisis.
Which brings us nicely to part 3, taming alarm fatigue.
Imagine for a second if your home smoke detector went off every single time you toasted a piece of bread. Eventually, you just get annoyed and take the batteries out, right? Well, that is the exact danger of alarm fatigue in industrial plant. To beat this, the industry relies on the ISA 18.2 alarm standard. It strictly defines an alarm as an audible or visible indicator of a condition requiring a response. That right there is the golden rule. A true alarm requires an action. If it goes off and you don't actually need to do anything, well, it's not an alarm. It's just noise.
And that noise leads us to a massive, massive problem: complex event cascades. Without proper management, a single complex event in a plant can trigger an absolute avalanche of nuisance and fluttering alarms. All that visual and auditory noise totally masks the actual root cause, completely overloading the poor operator. So what's the fix? Intelligent suppression, filtering that massive funnel of noise down to only the actionable alerts without ever compromising the safety of the entire system.
To do this, engineers use two primary suppression tactics: hiding, which is also known as shelving, and locking, which means taking an alarm out of service. And the technical difference here is absolutely crucial. Hiding a message temporarily moves it to a hidden list to keep the screen clear, usually during a routine stage change. But here's the key: hidden messages are still processed by the background system and permanently logged in the journal. Locking, on the other hand, is for equipment maintenance. When an alarm is locked, you'll see a white X, and it requires a stated operational reason. Locked messages are totally suppressed. They are not processed by the system, and they are not archived in the journal at all.
Now, for things like a planned plant startup, the system uses automatic hiding to keep things clear. It runs on a really brilliant 4-step mathematical logic sequence. Step 1 is the enumeration, where engineers define operating states, like normal or hiding, in the shared library. Step 2 installs the state representation, or steep block, which connects the state logic signals straight to those enumeration values. Step 3 is the block group assignment. This essentially links the steep block and the message-capable blocks together. And finally, Step 4 is the hiding matrix. This is where engineers configure the exact logic that dictates exactly which specific alarms are automatically suppressed during a specific operating state. It's like a perfectly choreographed dance.
All right, moving into part 4, the synchronization triad. Let's step away from the operator's control room for a second and look at a massive hidden technical risk. We call it the parameter desynchronization triad. Imagine an operator notices a process is running just a bit too hot. So, using their interface, they manually lower a limit from 375 down to 360. Great, the live server is now happily running at 360. But the offline engineering data block is still sitting there stranded at the old 375. The consequence? If an engineer compiles and downloads the offline program later without realizing this mismatch, the operator's live 360 setting will be disastrously overwritten. The system will revert right back to the outdated 375 state. To stop this from happening, the system relies on an absolute lifesaver of a feature, the readback function. Before the system even permits a full program download, it automatically prompts this readback requirement. What it does is safely copy the live parameter values, like that updated 360 limit, and pulls them backward into the offline engineering station. This successfully closes the loop, strictly preventing any accidental data loss, and leaves a highly precise audit trail showing exactly which individual inputs and outputs were updated. It's a real game changer for system stability.
Now for part 5, analytics and optimization.
So how in the world do engineers keep this massive nervous system healthy over the long haul? They rely on system analytics, specifically a super powerful tool called the message hit list. This gives engineers statistical visibility into all those archived messages. By sorting the data by things like message number, frequency, cumulative duration, and average duration, engineers can actively hunt down the most aggressive system offenders. The list defaults to sorting by descending frequency, so it instantly exposes which specific alarms are just triggering nonstop.
Because the reality of running a plant is that a tiny handful of nuisance alarms will completely dominate the system's bandwidth. You look at the data and might find that just 3 alarms, say a material tank level, a pump feedback error, and a valve fail to open, literally make up the vast majority of all incoming system noise.
Once the hit list exposes those worst offenders, engineers feed them straight into the alarm optimization loop. They run these nuisance alarms through some diagnostic filter questions, like does this actually require a human to intervene, or is this message just fluttering rapidly at its threshold? Depending on the answer, they apply targeted resolution measures. They might redefine and just eliminate the alarm entirely if no reaction is needed. They might recalibrate the mathematical hysteresis to stop the fluttering. Or, if it's a real persistent physical problem, they take the hardware route and literally go repair or upgrade the mechanical field sensor.
And finally, part 6, the message lifecycle.
Bringing our whole journey full circle, all of these discrete parts we've talked about actually form an infinite loop, the PCS7 message lifecycle. It kicks off in phase 1 with definition, configuring all those limits and enriching the code with associated values. Then it moves into phase 2, display and react, which is where operators are actually navigating the messages on their screens. Phase 3 is manage, using those ISA 18.2 standards to hard lock alarms for maintenance or smart hide them for operational clarity. And phase 4 is sync and optimize, where the readback function keeps everything consistent and those analytics hit lists drive the continuous tuning we literally just looked at.
If there is one crucial thing you take away from this explainer, let it be this. A robust industrial message system is never, ever static. It's not just software that you install once and forget about. It's a dynamic, continuously learning, continuously optimized loop. By rigorously managing alarms, preventing desynchronization, and analyzing the data, this architecture ultimately protects both the physical machinery of the massive plant and, most importantly, the people operating it. But as we wrap up today, I want to leave you with a bit of a provocative thought. We've seen just how much incredible automated logic is built into filtering, suppressing, and contextualizing these alarms before a human's eyes ever even see them. So, as industrial automation becomes infinitely more complex and artificial intelligence inevitably takes on more and more of this optimization loop, how much of the final safety decision should we continue to leave to the human operator sitting in the control room? It's a massive question and one the engineering world is going to be wrestling with for decades to come. Thanks so much for joining me on this explainer, and keep questioning the systems that run our world.